Bismillahirrahmanirrahim. Assalamu alaikum. Hello and welcome to lecture number 6 of Algebraic Topology. In today's lecture, we are mainly concerned with simplexes. We'll be trying to understand simplexes because simplexes provide a variety of examples for our further discussions. To understand simplexes, we need to understand what are affine subsets and affine spaces. So, starting with our first definition of affine subset, a subset A of Euclidean space is called affine if for every pair of distinct points x, x prime, the line determined by x, x prime is contained in A. So consider the example of plane and consider this set A of R2. Okay. So if I take any 2 points from this set A, so let's say this point and this point, then the line determined by these 2 points is contained in A, because the line determined by these 2 points is in fact this set A, and it is totally contained in A. Similarly, I can take any other 2 points and the line determined by this is exactly A, and which is contained in A. So we can say that this line A in R2 is a affine subset. So observe that affine subsets are convex. Okay, so in the definition of convexity, we impose the condition that the line segment joining any 2 points. Okay, sorry, this is not convex because the line segment joining these 2 points is not contained in the set. But let's consider this example. It is convex, and we impose the condition that the line segment joining 2 points is contained in the space. But over here we are requiring that the line determined by x and x prime. So in the Euclidean space, if we are in the Euclidean space, then we can determine a line passing through 2 points. So for example, if this set is in, let's say, R3, then if we are considering a subset and we want to show that it is a affine subset, then the line determined by these 2 points, which is an infinite line, should be contained in this. Of course, if this is this bounded, let's say, sphere, then this is not a affine subset because the line determined by these 2 points is not contained in this set. Okay. So note also that by default phi and 1 point subsets are affine. Let's consider another example. Take R2 as Euclidean space. Then affine subsets of R2 are either phi, singleton, a line, or R2. Okay. So why is singleton in R2? So let's say this is the point xy. So why this is affine? Because it has only 1 point, and the line joining this point to itself, of course it is contained in this set, and we have already seen that if I have a line in R2, then why this line is affine? Because if I take any 2 points, then the line determined by these 2 points is the same line which is contained in the set. So that's why this line is a affine subset. And similarly phi is affine because there is no point inside phi. So of course we can say that for any 2 points in phi, the line joining them is also contained in phi. If xj is a family of convex or affine subsets of Rn, then their intersection is also convex or affine. So it's a very simple result, but it's very important as well. So how do we show that? I'm going to show it for convex, and the proof for affine is very, very similar. So what is given? So the given is we have a collection of convex sets. So each of every xj is convex, and to show is their intersection xj is convex. So if I want to show that this set, which is the intersection of xj's, and the indexing set belongs to the capital J. So if I want to show that this set is convex, so what do I need to show? Take any 2 points, let's say x1, x2, belonging to this intersection xj, and I need to show that this implies the line segment joining x1 and x2. So the line segment joining x1 and x2 is tx1 plus 1 minus tx2 is also contained. Okay, so we can say that for every t, and we have this point belongs to j, belongs to capital J, xj. Okay, so for every t, this is a point of this set, or in other words, this line segment is contained in this intersection. So that's what we have to show. Okay, so since x1 and x2 belongs to the intersection, so this implies x1, x2 belongs to xj for all j. So for each and every value of j, x1, x2 belongs to xj. So since xj is convex, so this implies tx1 plus 1 minus tx2 belongs to xj for all t belongs to 0 to 1, and for all j's, for each and every value of j, these points or these points of the line segment joining x1 and x2 belongs to xj. So let's say this is xj, so x1 and x2 belongs to this. So when you take t is equal to 0, then it is basically x2. When you take t is equal to 1, then basically this is x1. So starting from this point to this point, this is the line segment joining x1 and x2, and this is totally contained in xj for each and every value of j. So let's say it is contained in x1 as well, because x1 and x2 are also element of x1, and similarly for x2 and for other values of j. So since this belongs to xj for each and every value of j, so of course this implies that tx1 plus 1 minus tx2 belongs to the intersection of xj as well for all t belongs to 0 to 1. Okay, so now what we have proved it, if I take any 2 points from this intersection, okay, then the line segment joining these 2 points is contained in the intersection. So we can say that the intersection is convex. After above theorem, now it makes sense to speak of the affine sets or convex sets in Rn spanned by subset X of Rn. So if it is the convex set spanned by some subset, then it is called the convex hull of X. Okay, so why it makes sense? So for example, now I can consider, let's say, points x1, x2 up to, let's say, xk, which is contained in Rn. So now these points are some collection of points of Rn. Now I can talk about the smallest affine set of Rn containing these k points. So the smallest affine set of Rn containing x1 up to xn, xk. Okay, so this smallest affine set containing these points is the affine set spanned by this thing. Okay, so why this smallest word and this intersection result? So why they are related? Because now I can say that smallest or the intersection of all affine subsets containing x1 up to xk is the affine subset spanned by x1 up to xk. Similarly, I can define the same thing by replacing this affine with convex, and in this case this is called the convex hull of X. So formally speaking, let X be a finite subset of Rn, then the convex or affine set spanned by X is the smallest convex or affine subset of Rn containing X. So we denote this by the square bracket X. We can also say that the square bracket X is the intersection of all convex or affine subsets of Rn containing X. So that's exactly the idea, and we are basically using this theorem to define the convex set or affine set spanned by some collection of finite points of Rn. Note that the square bracket X or the affine or convex set spanned by this finite set X does exist. So for example, if you can't find any subset of Rn which is the smallest subset, smallest affine subset containing these points or containing this set X, then of course Rn is always there. So Rn, of course, this contains X, and this is an affine subset. Okay, so similarly for convex set, and this Rn is also convex, so the convex hull of this capital X, if you can't find any, then of course Rn is always there. So convex hull always exists. So similarly the affine subset of Rn spanned by this capital X will always exist. It is hopeless to try to describe arbitrary convex subsets of Rn. For example, for every subset K of S1, the set D2 minus K is convex. Even closed convex sets exists in abundance. However, we can describe the convex set generated by X for finite X. So the point is, it's impossible to try to classify them or try to study them in a systematic way, because they are in abundance. So that's why we will only try to concentrate on the convex sets spanned by a collection of points. Our next definition is affine combination. An affine combination of points, some finite points P0 to Pm in Rn, is a point X which is equal to this expression. So T0 P0 plus T1 P1 up to Tm Pm, where there is a condition on the coefficients that sum of the coefficient is equal to 1. Similarly, we can define a convex combination. So this is an affine combination with the following condition, that Ti are all greater than or equal to 0, so they are all non-negative. Okay. So you can observe that we are running very parallel to the study of vector spaces. Okay, so we can define a vector space spanned by a collection of points, and similarly we also talk about combination of vectors. Okay, so in this particular case, when you impose the condition that their summation of the coefficient is equal to 1, so basically we are imposing a geometrical condition. So let's see, for example, if I take P0 is equal to let's say 1 0, and P1 is equal to 0 1, so in R2, so let's say if I have this collection P0 P1 in R2, then what is this point and what are the conditions? Okay, so this is the point 1 0 and this is the point 0 1. So an affine combination of P1 and P2 is something like this. Okay, so T0 P1 plus T1 P1. Okay, so this is basically equal to T0 1 0 plus T1 0 1, so which is equal to T naught and T1. Okay, so this is the set X, but then there is a condition on this as well. Okay, so if there is no condition on T naught and T1, then basically this is any point of the plane. So these two vectors, so we have seen from our study of vector spaces that as a vector space, these two P1 and P2 span the whole plane. In other words, every vector of R2 can be written as a combination of this. So as you can see that X is any general combination. T naught T1, I can vary T naught and T1 if we are studying vector spaces, and I will be getting points of this plane. But in the affine combination, there is also a condition that the sum of these coefficients should be equal to 1. So in other words, what we are saying is T naught plus T1 should be equal to 1. So let's say this is my T naught axis, and let's say this is my T1 axis. Now what does this condition mean? So this condition means that T1 is equal to 1 minus T naught. So basically it's a straight line in the plane. So what is this straight line in the plane? So basically it is a line passing through these 2 points. Okay, so in other words, what we are saying that X is a affine combination of these 2 points if we have this condition. So T naught plus T1 should be equal to 1. In other words, the condition on T naught and T1 suggests that the points X, which are the affine combination of P1, P naught and P1, are basically points on this line. Okay, so so there is a condition on T naught and T1, and this condition implies that we are getting points on this line. So this is the difference between affine combinations of 2 points in R2 and any linear combination that we studied in the discussion of vector spaces, that if we take this P1 and this P2, then their linear combination, every linear combination will be all the points of R2. But in this case, due to this extra condition that T naught plus T1 should be equal to 1, now we are getting points which are basically just a line in this R2. And similarly, we can impose another condition. So let's see if I have this point P naught and P1, and if I want to study the convex combination. So in the convex combination, there is another extra condition that all the Ti's should be greater than or equal to 0. So in this case, if we impose this condition that Ti's are greater than or equal to 0, so this is T naught axis and this is T1 axis. So in other words, we are saying that we are only in the first quadrant. In other words, this line segment, okay, so this line segment is basically the collection of all convex combinations of these 2 points. Okay, so of course, if I have one point, then this point on the line is convex combination of these 2 points P1 and P2. If I have another point, then this point is also convex combination of these 2 points. If another point, then this point is also convex combination of these 2 points. Okay, so that's the difference between linear combination in vector spaces and affine combinations. The affine set spanned by these m+1 points consists of all affine combinations of these points. Okay, so this is the result, and we are going to omit its proof. So it's just saying that, so what is an affine set spanned by m+1 points? So the affine set spanned by these points is basically, so affine set spanned by these points is the smallest affine set containing P naught up to Pm. Okay, so this is the smallest affine set containing these points, or in other words we can say that the intersection of all affine subsets of Rn containing P naught up to Pm. So we have already discussed this thing, but this theorem says that, so this affine set spanned by this, so let's say this affine set spanned by this is X, so this consists of all affine combinations of these points. Okay, so this X, which is the smallest affine set containing these points, so what are its elements? X such that X is equal to T naught P naught plus T1 P1 plus T2 P2 up to so on plus Tm Pm, and there is also a condition on the Ti's that their sum I is equal to 0 to m should be equal to 1. So this set is the collection of all affine combinations. Okay, so for all Ti belongs to reals, and this set, which is the collection of all affine combinations of P naught up to Pm, is in fact the affine subset spanned by P naught up to Pn. So which is very important result. So now we can compute the points of the affine subset spanned by collection of points. So once again you can see a very similarity between this study and the study of vector spaces, but of course there are some differences. So for example, we have imposed this condition, and we have already seen that due to this condition we are restricting the points, and this is not exactly the same as vector spaces. So an ordered set of points is affine independent if P1 minus P naught, P2 minus P naught up to Pn minus P naught is linearly independent subset of the real space Rn. Okay, so any linearly independent subset of Rn is a affine independent set. Okay, so for example, if I have P naught up to Pm linearly independent subset of R, let's say n, where of course m plus 1 is less than or equal to n. Okay, so we have some linearly independent subset of Rn. Now of course P1 minus P naught up to Pm minus P naught are also linearly independent, because if they are not linearly independent, then this set is also not linearly independent. So it is a little exercise for you that this implies this set is linearly independent. So for example, you can try to show that on contrary assume that this is linearly dependent, and let's see if you come up with some contradiction then that this set is also not linearly independent then. So this is a simple example of affine independence. Okay, so once again you can see a difference of this definition of affine independence and linearly independence of vector spaces. Okay, so converse of above is not true, because any linearly independent set together with origin is affine independent and not linearly independent. So for example, in R3, for example, if I take 1 0 0 0 1 0 and 0 0 1 and another point 0 0 0, so this collection is not linearly independent. So linearly independent as a vector space, so we are taking these 4 vectors of this vector space R3 and we are saying that they are not linearly independent. Of course they are not linearly independent because we can choose 0 1 0 0 plus 0 0 1 0 plus 0 0 0 1 plus, let's say, any number, let's say 1 0 0 0, and answer is still 0 0 0. So this is linearly independence means. So in general it means that set of vectors v1 up to vm is linearly independent if a1 v1 up to so on am vm equal to 0 implies that all the coefficients are 0. So in this case we can choose coefficients which are not all 0 but still the combination is 0. So we can say that these are not linearly independent or linearly dependent. But for affine independence, what do we need to check? So we need to check that, for example, if I take this point as p0, this is p1, this is p2, and this is p3. So let's calculate what is p1 minus p0. Of course this is the same point 0 0 1, and now let us calculate what is p2 minus p0. So this is equal to 0 1 0, and what is p3 minus p0, so this is equal to 1 0 0. So in this case the collection p1 minus p0, p2 minus p0, p3 minus p0 is basically equal to the set 0 0 1 0 1 0 and 1 0 0. So we know that this set is linearly independent, and so according to the definition of affine independence, this set p0 p1 p2 p3 is affine independent, but this set is not linearly independent. A set p0 p1 is affine independent if p0 is not equal to p1. Okay, so a set p0 p1 p2 is affine independent if it is not collinear, and of course a set p0 p1 p2 p3 is affine independent if it is not coplanar. Okay, so for example, if these 4 points are coplanar means if they are contained in the same plane, let's say this is p0 p1 p2 p3, and then of course these vectors p0 p1 p0 p3 and p0 p2, so these 3 vectors are not linearly independent, because we know that in plane 3 vectors are not linearly independent, because in R2 2 vectors are at most linearly independent. Okay, so similarly a set p0 p1 p2, okay, so let's say they are on the same line, so p0 p1 p2, so now the vector p0 p1 and the vector p0 p2, okay, so these two are not linearly independent because of course they are parallel and they are scalar multiple of each other. The following conditions on an ordered set of points are equivalent. So if these are affine independent, then it satisfies the following condition. So for any collection S0 S1 up to Sm, if this linear combination is equal to 0, Si Pi is equal to 0, and their summation is equal to 0, then all the Si's are equal to 0. So once again you can see the similarity of this discussion with the discussion of vector spaces. So in vector spaces we show that some collection of vectors v1 up to vn are linearly independent if a1 v1 up to so on plus am and vn is equal to 0. This implies that these ai's are 0 for all I. But over here we are saying that this combination, so S0 P0 up to so on SM PM equal to 0, also if the summation S0 up to so on SM equal to 0, then this implies S0 equal to S1 equal to SM equal to 0. So this is the extra condition that we impose in this case. So this is the difference between the discussion of vector spaces and affine spaces. Okay. So similarly, for each x belongs to A, the affine set spanned by this has a unique expression as an affine combination. X is equal to Ti Pi, and the summation of Ti is equal to 1. So once again, in the vector space cases, if we have a vector space or a subspace spanned by these vectors, then every element, if I take some element, let's say another vector W, then this W can be written as a unique combination of, let's say, alpha 1 V1 up to so on plus alpha n Vn. Okay, but in this case, if I take an arbitrary element from A, which is basically the affine set spanned by these points, then this X has this unique combination. Okay, so these Ti's are unique, and these Ti's satisfy this extra condition. So this extra condition have some geometrical meaning, which we have seen in a very particular example. If A is the affine set in Rn spanned by an affine independent set, then A is a translate of an m-dimensional subvector space V of Rn. So namely, A is equal to V plus x naught. So this kind of relates, so this corollary relates the study of vector spaces and the study of affine spaces. So it says that if we have a space A which is spanned by some collection of affine independent set, then A is the translate of m-dimensional subvector space V of Rn, namely this. So the proof of this is very simple, but it's irrelevant, so that's why we are going to omit this thing. So, but this corollary is important if you want to understand the relation between the affine sets spanned by some collection of points and the vector spaces spanned by some collection of points. Okay. So a set of points is in general position if every n plus 1 of its points form an affine independent set. So if n is equal to 1, what we are trying to say that any pair of points is different. Okay, so any pair of points is affine independent means that AI is not equal to AJ. So any two points are different if we want to say that these are in general position. Okay. So similarly, if n is equal to 2, or in other words, if we are in R2 and we want to say that some collection of points are in general position, so what we are trying to say that is that no 3 points are collinear in that set. Similarly, if you are in R3 and if you say that some collection of points, let's say A1 up to AK, so they are in general position, then basically what you are trying to say that no 4 points, so 3 plus 1, 4 points, so no 4 points are coplanar. So we have seen that so 4 points are affinely independent if and only if they are not coplanar. For every k greater than or equal to 0, a Euclidean space Rn contains k points in general position. So we'll be needing this result in our further discussion. So this result, and of course we are going to omit its proof because it's irrelevant to our discussion. So this result confirms that if I have any k which is greater than or equal to 0, then the Euclidean space Rn contains k points in general position. So we will be using this result in our further discussions. So let P0, P1 up to Pm be an affine independent subset of Rn, and let A be the affine set spanned by this subset. If X belongs to A, then above discussion tells us that there is a unique m plus 1 tuple T1 up to Tm with these conditions. The entries of these m plus 1 tuple are called barycentric coordinates. So if I have a collection of m plus 1 points and they are affinely independent, and A is basically a affine set spanned by this subset, then we know that from our above discussion that any x belong to A can be written in this form, and these TIs satisfy this condition, and these TIs are unique. So we call these values of TIs, so T0, T1 up to Tm, as the barycentric coordinates of X. Okay, so it has some very geometrical meaning, but we are not going into the details of these barycentric coordinates because this is irrelevant to our further discussion. But the point is, similar to the vector spaces, if I have a vector V belongs to a vector space, then corresponding to a chosen basis, so let's say it has some basis V1 up to Vn, and this is equal to V, and this small v is an element of V, then there exists unique, okay, A1 up to An, such that V is equal to A1 V1 up to An Vn. So we can say that A1 up to An are the coordinates with respect to this basis. So instead of using the word coordinates, we are using the word barycentric coordinates. So once again, it has some reasons behind it, but it is irrelevant to our further discussion, so we are going to avoid it. Okay. So let P0 up to Pm be an affine independent subset of Rn. The convex set spanned by this set, denoted by square brackets P0 up to Pm, is called the affine M simplex with vertices P0, P1 up to Pm. So observe that there is a difference between this definition and the definition of the affine set spanned by these points. Okay, so what's the difference? So this theorem will clear the differences. So if we have a collection of points and these are affinely independent, then each x in the M simplex has the unique expression of the form. So this is similar to the affine case, but now we are imposing the condition that each Ti is greater than or equal to 0 as well. So once again, we have already seen this example where we took this P1 to be 1, 0 and this P2 to be 0, 1, and the affine subset spanned by these 2 points is basically this line, but the convex set spanned by these 2 points is basically this line segment, because here we impose the condition that Ti's are greater than or equal to 0. So if this is T0 and this is T1 coordinate axis, then this Ti greater than or equal to 0 means it has to be in the only first quadrant. So this is the difference between affine combination and convex combination. Barycenter. So if we have m plus 1 points and they are affinely independent, then the barycenter of these points, so barycenter of this M simplex, affine M simplex, is defined in this way. Okay. So P0, so the simplex generated by 1 point is a 0 simplex and consists of only 1 point, and which is its own barycenter. So for example, if we have just 1 point, then the M simplex generated by this is just the point itself. So if we have 2 points, then we will have 1 simplex, and the 1 simplex is basically the closed line segment with endpoints P0 and P1. So let me remind you once again this example in R2. So the line segment joining P1 and P2 is this. So this is basically the 1 simplex, or the convex set generated by these 2 points P1 and P2 in this case. So similarly, if we have any 2 points in the plane, then the line segment joining them, so let's say this is P0 and this is P1, then the line segment joining them is basically the 1 simplex generated by these 2 points. And the barycenter in this case is half P0 plus P1. So basically it's going to be the midpoint of the line segment. The 2 simplex generated by 3 points is a triangle with interior. Okay, so with vertices P0, P1, P2. Okay, so let's say this is my point P0, this is point P1, and let's say this is point P2. then the 2 simplex is the triangle, and the interior is also part of this 2 simplex. Of course, if its interior is not part of this simplex, then it is not going to be convex set. So the barycenter in this case is 1 by 3 P0 plus P1 plus P2. So if this is an equilateral triangle, then this is going to be exactly the middle point. But this barycenter is basically, you can say, that center of mass of this triangle. So note that the 3 edges, P0, P1, so this is the first edge, P1, P2, the second edge, and P0, P2. Okay, so now P0, P1 is the edge opposite to P2. Okay, and it is a 1 simplex. Okay, so P0, P1. So we know that 2 points generates a 1 simplex. Okay, so thus a point on this edge has barycentric coordinates t1 minus t0, because there is no contribution of P2 in this case, and we also know that from our previous result, let's go back to that result, that each x in the M simplex generated by these affinely independent points has the form Ti Pi, where of course there are conditions on the Ti's that they should be non-negative and the sum of Ti's should be equal to 1. So using this result, we can say that each and every element of this triangle should be of the form A0 P0 plus A1 P1 plus A2 P2, but there are some conditions. So the first condition is A0 plus A1 plus A2 should be equal to 1, and AI should be greater than or equal to 0. So with these conditions, so these are all the points, and AI varies on the real number. So under these conditions, so these are all the points, but if we are taking only this simplex generated by P0 and P1, then we should take this A2 to be equal to 0. So the elements of the 1 simplex generated by P0 P1 are basically A0 P0 plus A1 P1, and of course A0 plus A1 equal to 1, and these AIs are greater than or equal to 0. So this expression says that we can find the value of A1 to be equal to 1 minus A0. So if A0 is t, then A1 is 1 minus t. So if A0 is t, then A1 is 1 minus t. Okay, so I can take this A0 to be some other, so basically it's a dummy variable, so I can replace this A0 with t. So that is the coordinate t2 is 0. Of course in this expression there is no coefficient of p2. So more generally, t0, t1, t2 lies on the edge if and only if one of its coordinate is 0. So we are going to need this observation. So this is the edge of the triangle, and we are saying that if a point of the triangle is on this edge, then one of the coordinate is 0, in this case P2 is 0, and if some point is on this edge, then of course the coefficient of P1 is 0. If a point is on this edge, then of course the coefficient of P0 is 0. So after all, such points are convex combinations of the endpoints of their respective edges. So the 3 simplex, P0, P1, P2, P3. So we have 4 points which are affinely independent in R3 is a solid tetrahedron with vertices P0, P1, P2, P3. Okay, so it will look something like this. So also the interior of this tetrahedron is also part of our simplex. Okay, so the triangle has faces. So for example, these are the points. So 1, 2, 3, 4. So these 4 points, so let's say P0, P1, P2 and P3. So these 4 points generate this convex set, and each and every point of this tetrahedron, and inside this tetrahedron, this solid tetrahedron, so will be of the form A0, P0 plus A1, P1, A2, P2 plus A3, P3. Okay, and of course there are some conditions that A0 plus A1 plus A2 plus A3 is equal to 1, and all the AIs are greater than or equal to 0. So under these conditions we can have this tetrahedron. So if this is P naught, if this point is P naught, then this simplex is basically generated by P1, P2, P3, and it's a triangle. We have seen that a simplex generated by 3 points is a triangle, so we can see that it's a triangle, so solid triangle. So a two-face, so we can say that it's a two-face because it is a two-dimensional face. So similarly there are other faces as well, so we will see that of course this, if this is P naught, let's say this is P1, then this face is generated by P naught, P2, P3. Okay, so similarly we can find other faces of this tetrahedron as well. So how many faces there are? So 1, 2, 3, 4 faces. So in each and every face I am just deleting one of the coordinates. So deleting P naught will give me this face, deleting P1 will give me this face, and up to so on. So for I is equal to 0 to n, let EI denote the point in Rn plus 1 having Cartesian coordinates all 0 except 1 in the I plus 1's position. So let's consider a set E naught up to En, and the points E naught, E1 up to En are defined in the following way, that E naught has 1 at the first position and rest of the coordinates are 0. So similarly E1 has 1 at the second position and rest of the coordinates are 0, and similarly we can define what is En, so 0, 0, 0 up to 1. Okay, so rest of the coordinates are 0. So these are affinely independent because these are points of Rn plus 1, and basically this is standard basis of Rn plus 1, so of course they are linearly independent. If these are linearly independent, then we can also say that E naught up to En are affinely independent, because we have observed that if a collection of points is linearly independent, then there are affinely independent as well. Okay. So in this case barycentric and Cartesian coordinates coincide, and the simplex generated by these points is denoted by this delta n and called the standard n simplex. So for example, if I have R3, so in R3 let's say this is x-axis, this is y-axis, and this is z-axis. So this is E naught. Okay, so this E naught is equal to 1, 0, 0. E2 is equal to, sorry, E1 is equal to 0, 1, 0, and E1 is equal to 0, 0, 1. Okay, so basically now the simplex generated by these 3 points is going to be the triangle. Okay, so this triangle, so this is the 2 simplex generated by these 3 points. Okay, so we call this the standard n simplex. So faces of a simplex. So let P naught up to Pn be an M simplex. The face opposite to Pi can be computed in the following way. We have already seen that you just need to delete the coefficients of Pi, or in other words, over here you just delete Pi and the coefficient of Pi is 0, then this is the face opposite to Pi, and the boundary of this is the union of its faces. So once again let's have a look at the example of this tetrahedron, solid tetrahedron. So the face opposite to this is this simplex, the face opposite to this is this simplex. So the boundary of this simplex is the union of its faces. So the boundary of this tetrahedron is union of this triangle, this triangle, this triangle, and this triangle. So if you take union of these 4 solid triangles, then it will be the boundary of the tetrahedron. Clearly an M simplex has M plus 1 faces, and for an integer k we can also define this thing, that take k to be any number between 0 and m minus 1. One sometimes speak of a k face of this. So namely a k simplex spanned by k plus 1 of the vertices. So in this terminology, the faces defined above are m minus faces, because we have taken k to be equal to m minus 1, and basically these are m points. Okay. So for example, once again let's have a look at the example of tetrahedron. So this is the two face. So now I can define a one face as well, so generated by 2 points. So if I take this point and this point, then the convex set generated by these 2 points is this line. So this is the one face, and similarly I can take 1 point, and this is going to be the zero face of this tetrahedron. So our last definition of today's lecture is, what are affine maps? So if we have m plus 1 points and they are affinely independent, and let A denote the affine set it spans, the affine map T from A to Rk is a function satisfying this condition. Okay. So T, when we apply T on T naught, P naught up to T m P m, then this is equal to T naught T of P naught plus Tm T of Pm. Okay. So where of course this is a affine combination, so the summation should be equal to 1. The restriction of T to this simplex is called an affine map. So we can define this map from any affine set, and since this simplex is contained in this A, so this is also called affine map if we restrict this map to this M simplex. Thus affine maps preserve affine combinations, hence convex combination. So you can see that these TI's are not changed when I apply T on this affine combination. Okay, and this relation of course is not changed, so we can say that they preserve affine combination. And of course convex combination, because in convex combination everything remains same, and there is extra condition that these TI's are greater than or equal to 0. It is clear that an affine map is determined by its value on an affine independent subset. So of course if we know what is T of P naught up to T of Pm, then we can find images of any point of A under this T. So moreover, uniqueness of barycentric coordinates relative to P naught up to Pm shows that such an affine T exists, since the formula in the definition is well defined. Okay, so we can see the similarity of this discussion with the similarity of linear transformations in vector spaces. Our last result of today's lecture is, if we have an M simplex generated by these P1, P naught up to Pm points, and if we have another N simplex, and if we have a function from P naught up to Pm to Q naught up to Qn, so from this set to this simplex, then there exists a unique affine map such that this holds. Okay, so the proof of this result is very simple. So the points of this M simplex are of the form Ti Pi, where I is equal to 0 to M, and of course the summation of these Ti's from 0 to 1 M is equal to 1. So there is a unique affine transformation. So T when applied on Ti Pi, so according to the definition, so this should be equal to summation Ti T of Pi. So these images are unique, and so this transformation is unique. Okay, so this is the end of the result. So this is the end of the lecture. Thank you very much, and Allah Hafiz.